Every time a comet's tail changes shape, questions begin. Is it a breakup, a new jet, or just an optical illusion? Atlas 3I shows twists and knots, sometimes with a broad curve, sometimes with a faint straight jet. The reason is developing two different tails at once. We unpack the difference between dust and iron tails and reveal how nucleus rotation and solar wind pressure can sculpt the sky. No exaggeration, just what the images really suggest. Power. What would change a comet's tail shape from one image to the next? If you've wondered whether that means a breakup, new jets, or simply a viewing angle, you're in the right place. In this video, we'll break down the main drivers: dust tails versus iron tails, solar wind pressure and rotation, and we'll show you what to look for in the latest frames of Atlas 3I. No exaggeration, just what the images likely indicate, what's uncertain, and what upcoming observations might confirm. Why can a comet develop two different tails at once? In recent frames, 3 Atlas shows a twisted streak in one shot and a straighter, fainter jet in another, because a single object would draw two signatures in the sky. Let's start with the two types of tails a comet can have. A dust tail is composed of small solid grains released from the surface. Sunlight pushes those grains with gentle pressure, so the trail tends to bend and arc along the comet's path. An iron tail different. Gas escapes, loses electrons from sunlight, and those charged atoms are picked up by solar wind, which is a stream of particles flowing from the sun. That tail often appears straighter and sits slightly off the motion line because the wind sets its direction. Here's where it gets complicated. Dust and iron tails don't have to point in the same direction and rarely illuminate at the same time. In one image, the curved dust tail may dominate. Minutes later, a modest change in background. Exposure or solar wind can make the straight iron tail stand out, while the dust arc appears stable or even fades. That discrepancy can make consecutive photos look like two different comets when they're just two materials responding to two forces. A clear example appeared with comet Neowise in 2020. The curved dust tail looked warm and broad in most photos, while a thin straight iron tail appeared displaced. Short exposures captured the bright inner curve and hid the faint blue line. Longer exposures brought out the straight jet and subtle structures within it. That same exposure effect can occur in 3 Atlas frames, so one photographer can capture bright twisted arc and another can reveal a faint rigid line minutes later. Solar wind conditions add another layer. Wind speed and direction vary with solar activity. When a high-speed stream from a coronal hole passes, the magnetic field carried by that flow can pull the iron tail toward a new orientation within hours. That requires no change in the nucleus. It's the environment changing the charged gas downstream. Dust, however, reacts to sunlight and orbital geometry, so it evolves on slower timescales and maintains that elegant curve, even while the iron tail swings. Think of dust as confetti in a flashlight beam. Confetti drifts outward and curves as it spreads. Irons behave more like smoke caught by a fan that changes speed. When the fan blows, the smoke line bends quickly. When the fan calms, the line relaxes. Grain size also matters. Radiation pressure, the push of sunlight hits harder on small particles than large ones. Tiny grains push quickly and create thin, sharp features. Larger grains lag behind, spread more and hold brightness longer. This size sorting builds a broad, slowly changing dust tail. If you see a steady arc that barely shifts during a night, large grains likely play a role. Meanwhile, the iron tail formed by much lighter irons shows faster geometric changes because it's tied to the wind and its magnetic field. Apply these rules to 3 in Atlas. If a slightly displaced straight tail brightens or moves while the curved arc remains nearly the same, a working hypothesis is that the iron tail is responding to a wind change rather than a breakup. A sudden bend in the straight tail followed by a clean section downstream also fits normal iron tail behavior. In contrast, a dust tail fracturing into multiple persistent arcs would raise questions about new dust sources. So the small reward is simple. Marked differences from one frame to another can be normal behavior. Two tails are writing two stories at once, each with its own clock and compass. If your next image shows a faint straight line where the last showed a bright arc, that may be the iron tail manifesting while the dust tail keeps its slower pace. Next, we test whether rotation, focused jets, or true fragmentation might be behind the more pronounced twists and knots that some frames suggest. Rotation, jets, or breakup. What structures really suggest? One frame shows a twist and knot. The next shows a faint split. Does that mean 3i Atlas is shedding fragments or just rotating? The quick answer is both signals can look similar in still images. To differentiate them, we need to talk about jets and rotation in simple terms and then test what the most recent frames show. Jets are narrow streams of gas and dust emerging from active spots on the comet's surface. Sunlight heats a zone, ices vaporize, and escaping gas drags grains with it. Nucleus rotation is the spin of the solid core. As the comet spins, different jet sources face the sun, activate, or fall into shadow. That rotation paints patterns in the region near the nucleus and along the tail. A rotating jet can produce a spiral or corkscrew trail when seen from the side, or set of twists when viewed at angle. Here's the challenge. A compact, bright clump in the tail may look like a fragment that broke off, but it can also be a denser puff from a jet that rotated into view. Observation geometry matters. If we observe from slightly different angles on different nights, structures align or blur. Exposure time also matters. Short exposures favor the bright inner coma and knots near the nucleus. Long exposures connect those knots with fainter filaments and can reveal straight iron tail strands that mimic a split. A useful case study comes from comet 67P Churyumov-Gerasimenko. Its rotating jets produced hour-to-hour changes, including spiral textures and episodic puffs, even when the nucleus remained intact. The lesson is that rotation plus localized activity can generate sharp features without any breakup. For 3 Atlas, a similar rotating jet scenario is a reasonable first check because it explains rapid repeated changes without requiring a new body to appear. Another clue is a tail disconnection event. That's when part of the iron tail appears to break off, leaving a gap followed by a newly formed straight tail. The general opinion is this comes from a change in the solar wind's magnetic field, not from a split in the nucleus. When the field changes or a boundary passes, charged particles detach from the magnetic connection and the iron tail reforms aligned with the new field. If you see a clean gap followed by a sharp straight segment that supports magnetic reconfiguration rather than comet structural failure, then what should we check in 3I Atlas images? Follow a suspicious condensation, the bright spot that appears separate from the nucleus. If it maintains constant offset and moves with the same apparent motion as the comet over several nights, that's stronger evidence of a fragment. If instead it fades, elongates along the tail, or changes position with exposure and processing, it's more likely a jet-induced knot. Watch orientation. Features that remain attached to the tail axis and extend downward usually belong to flow, not a separate fragment. Photometry also helps. A photometric light curve is a brightness record over time. If jets rotate in and out of sunlight, total brightness often rises and falls with a repeatable period. A periodic light curve supports a rotation-driven pattern. No clear period doesn't prove no rotation, but weakens the argument that jets alone set the structure you see. Now apply these tests to recent frames. Are we seeing a compact condensation that persists and follows the comet night after night? Or a stationary knot that sits on the tail axis and transforms with wind changes? If features reset after a disconnection-like gap, solar wind likely played the main role. If they repeat at the same rotation phase, jets fit well. The small reward is this: most rapid frame-to-frame changes in C Atlas point to rotation and changing solar wind conditions. A breakup remains a hypothesis until a secondary in co-motion is measured across several nights with working explanations in hand. The next step is to look for a stable drifting companion, check for a repetitive brightness period, and watch for space weather updates that might shift the iron tail again. Conclusion: the rapidly changing shapes in 3 Atlas fit the overview. 2 tails responding to different forces, plus a spinning nucleus that turns jets on and off. A breakup remains a hypothesis unless a secondary condensation in co-motion is confirmed across several nights. Watch new images from NASA and ESA solar observatories and community observatories. Compare the displaced straight strand with the broader curved arc. Record any knot that maintains the same separation and motion as the nucleus. Stay curious and prioritize evidence. Careful notes on angle, exposure, and timing will help. What we learn now will improve how we interpret first light from the next interstellar visitor.